Hey, North Mr. Earler here. This video is going to go into valence bond theory. We're going to get into what's called hybridization in a later video. So it's kind of hard to talk about valence bond theory without hybridization, but we're going to kind of try and dance around that a little bit. So this will just kind of be a quick introduction into how these valence electrons actually bond. All right, so here's some key terms that we're gonna use a lot. We're going to talk a lot about overlap, the overlapping of electron orbitals to form a bond. There's lone pair and bonding pair, which you've seen before. The hybridization and hybrid orbital terms, go ahead and get those written down. We're going to be using those a lot, but just not yet in this video. And then sigma bond, this is the symbol sigma, and a pi bond. So once you have all of those terms written down, then we're ready to move on. We've used a couple different molecular models, or we will use a couple different molecular models, to talk about how atoms actually bond to form molecules. Lewis dot is the one you're most familiar with that we've been using already. And here, the Lewis dot really helps us kind of account for all of the different electrons. And it's really good at helping us to predict double bonds and triple bonds. And it gives us a little bit of the shape of the molecule. From the Lewis dot, we go to the VSEPR theory, which kind of builds on the Lewis dot and helps us kind of visualize these molecules in 3 dimensions, allowing us to predict bond angles and so forth as well. Now, the valence bond theory kind of goes into a little bit more depth on how these bonds are actually formed. So far, all we've said is that there's just a double bond here, right? We draw 2 pairs of electrons. It's important to keep in mind, though, that it's not the case that these electrons are just 2 particles that are just kind of sitting in between these 2 atoms, right? Electrons are not really, can't really be thought entirely of particles at all, right? They can be thought of as more of almost like a wave. And we can think of an electron cloud density, right? And so there's different regions around the atom where there's higher density of electrons than other regions, right? And the valence bond theory says that when these orbitals, when these areas of electron density overlap between 2 adjacent atoms, that's what actually forms the bond. It's 2 electrons of opposite spin coming together and kind of completing each other, completing like almost like a shared orbital. Remember that the p orbital looks kind of like this. There's 3 different orbitals, and they're kind of they each kind of have 2 lobes, right? So they're on the 3 different axes: px, py, and pz. So if we think of one of these sets of p orbitals from one atom, maybe a carbon atom, and one of these sets of orbitals from another atom approaching each other, then their orbitals are going to overlap. Which orbitals are going to overlap first if they approach each other horizontally like this? It would be the px, right, the pink ones, because they're sticking out in that axis, right? If we continue to bring them closer together, then now we create the possibility that the pz or the py could overlap as well. That's what this image is trying to show. I like how this is showing the electron spin up and down. So like an upspin from one atom is paired with a downspin from the other atom. The electron clouds are kind of like almost bending towards each other to become overlapped. All right, sigma and pi bonds. This is the technical definition of a sigma bond. It's a bond on the bond axis, along the bond axis. It's easier to just remember that the first bond is always a sigma bond. There's a couple different ways this can happen. We could overlap 2 s orbitals, and that represents a sigma bond. It's a bond on the axis of the 2 atoms. You could also do this with 2 p orbitals, which is an example shown here. What you have to remember is that the first bond is always the sigma bond. Any additional bonds are pi bonds, okay? So a bond that occurs above or below, or you could think of behind or in front of the bond axis, that is going to be called a pi bond. So you can see what we kind of mean by that, right? This bond up here is above the axis of the 2 atoms, and so it's a pi bond. So what you need to remember is that the pi bond is the second bond or the third bond if there's triple bond. The pi bond is weaker, there's less overlap, and it increases the rigidity of the molecule. You can, if all that's overlapping is the green here, then you can almost kind of picture that molecule twisting, and it would still be overlapping in the green region. But if the blue region up above and below is also overlapping, now you can't twist the molecule and still overlap those orbitals, and so it increases the rigidity of the molecule. As I said before, a double bond would be made up of one single sigma bond. The first one is always a sigma, and the second one is always pi. Here's a good picture to kind of show that small amount of overlap in the p orbital and the pi bond, and kind of another picture, almost kind of like that first one that I showed you, where it kind of shows the p's kind of bending towards each other almost. Single bonds are sigma bonds. So anytime you have a single bond, which is in any bond, you have one sigma bond at minimum, right? You might have additional pi bonds on top of that. But the single bond is always a pi bond. The double bond is a sigma with a pi. So then a triple bond is going to be a sigma. The first bond is the sigma. This is the yellow region. And there's two pi bonds in here. The blue orbital is overlapping both above and below, and the purple orbitals are overlapping both kind of in front and behind the axis. Bond order, we've seen this before, so I'm not going to spend a lot of time on this. The bond order is kind of a fancy way of saying how many bonds there are, right? So the bond order of 2 would be double bonds. And we've seen this before as well. The higher the bond order, the shorter the bond length, and the stronger the bond. And just keep in mind that you can have a third of a bond if you have a resonance structure that has one double bond and 2 single bonds. Then you would say that each bond is 1 1/3. The bond order would be 1 1/3. This kind of makes sense. As the bond order increases, the length decreases, and this picture kind of shows that pretty well. The more overlap you have, the shorter the bond. The atoms are physically getting closer to each other, right? The nuclei are getting closer to each other with more electron overlap. And also, the smaller the atoms, the shorter the bond. If the atoms themselves are physically smaller, then they can physically get closer to each other, right? There's less kind of in the way. The energy levels that are overlapping are closer to the nucleus. Whereas if you get out to like the 7th energy level, now the s orbital is way out there, and you're not going to share electrons very close to the nucleus. So take a look at this example and kind of soak this in for a second. The carbon-carbon triple bond is 120 picometers, but the carbon-hydrogen single bond is 106 picometers, right? The more overlap, the shorter the bond. The triple bond has more overlap than a single bond, but smaller atoms also make shorter bonds. The hydrogen atom is so small that this bond length is actually smaller than the carbon-carbon bond, even though the carbon-carbon bond is triple bond. Here's another good picture that kind of shows that. HF compared to HI, I is a much larger atom, and so the bond length is going to be longer, even though it's still with hydrogen, right? And they're both single bonds, but because the iodine atom is so much larger, that's a longer bond. It's therefore a weaker bond. Compare diatomic fluorine to diatomic iodine, right? Again, they're both single bonds, so they have that in common. So that's not going to affect the bond length. What affects the bond length here would be the size of the atom. Fluorine is a much smaller atom, and so it has a shorter bond length. The atoms are, when they overlap, the atoms are physically closer to each other, right? Fluorine would be overlapping in the 2nd energy level, whereas iodine would be overlapping, I think, in the 5th. So valence bond theory is trying to help us understand how exactly these bonds are being formed, right? And we understand this from the perspective of overlapping orbitals, okay? The more overlap there is, the shorter the bond, the stronger the bond. And the smaller the atom, the shorter the bond as well. If you have any questions on any of that, as always, write them down, and we'll get some practice in class. All right, this is Mr. Yergler, signing off.